Hi everyone, welcome to today's coding session. Today I'll be solving the house robber problem using Python. I will explain the problem, its constraint, and the approach we'll be using. We will explore two efficient methods, bottom-up dynamic programming and optimized DP approach with constant space. These approaches will help us maximize the amount of money we can rob without alerting the police. As I go, I'll explain each step in detail. Let's get started. So we're given a nums array where each element represents the amount of money in the house. We need to determine the maximum amount of money we can rob while following these rules. We cannot rob two adjacent houses to avoid triggering the alarm, and we must find an optimal strategy to maximize amount of money we steal tonight. So here, example 1, we can take one step and then skip, and that'll give us 4, or we can skip, and that gives us 3. So we know that 4 is greater than 3. So it's better to take one step and then skip. And that's why we output this. Same thing for example 2. We can take one step, then skip and skip, which will give us 12. Or we can skip and skip, which will give us 10. Again, 12 is greater than 10, so we'll go for 12. That's what we're going to output. So here are key constraints. We have at least one house and at most 100 houses. So our solution should efficiently handle up to 100 houses. Each house can contain between $0 and $400, meaning some houses might have no money. And here's the algorithm for our code. We're going to maintain a structure to track the maximum amount that can be obtained at each step. And at each decision point, we're going to choose between skipping the current house or robbing it and adding its value to a previous best outcome. We'll build up the solution iteratively, ensuring that no two adjacent houses are robbed. The final results represent the maximum amount that can be collected without triggering the alarm. And again, this is another example showing you the same step. We either skip and skip. And for these both examples, we're skipping. And here I'm just presenting you the difference between memorization we could have used, but we didn't. It's just another approach. Or tabulation. So we're using the tabulation bottom-up approach. So this approach will maintain an array DP where each element DPI stores the maximum amount of money that can be robbed up to the house I. So here's the Python implementation. So first we're going to check if the array is empty. If it is, we know we're not going to be able to make any money. Second, we're going to check the length of the array, which instead of checking here, let's just say n equals length nums. And we're going to see if the length of the array is 1. If that's the case, that means there's only one house and we're going to return. We're only going to rob that house. And next, we're going to initialize DP, which is what we were going to use to see whether we're going to skip the houses or take our first step to maximize our choices. And we're going to initialize this to the length of how many nums we have, the length of the array that we were given. And then we're going to initialize the index 0 with num 0. We're going to initialize the first index to the maximum value, since our whole goal is to maximize how many houses we robbed or how much money we get from the houses we robbed while not triggering any alarms. So at this point, our first decision is to choose between taking one step or skipping to step 1, to index 1. And now we're going to iterate so we can automate this approach. And range is going to start at step 2, since this is index 0, index 1, so that's the reason we start index 2. And it's going to go all the way to n minus 1, since range starts from 0 all the way to n minus 1. And then now we're going to initialize each step. So in order to do so, we're going to do the same thing that we did here. The only difference is that we're going to use DP, which in this case this right here is a scenario that we take one step. Here is the current nums and then meaning the current house based on the index. And here we want to also use DP, but now we are simulating that we're taking 2 steps. And once we're done with this loop, we're going to return how much money we made by returning the last element in DP in the tabulation we just created. So let's see if there's any issue with this code. All right, there we go. So properly indented, nums is correct. All right, so as you can see here, it beats 100%. So it's very efficient. Memory, it's not so much. Let's see if the other approach, it's going to be better, more memory efficient. But first, let's see a sample walkthrough. So here, as mentioned, if the num array is empty, we're going to return 0. Otherwise, we're going to move on. If we only have one house, we're going to rob that one house. Now we're going to initialize n with how many houses there are. Then we are going to create an array to include the houses, how many houses we have. So this way you have the same size for DP as the nums array. And now we're going to initialize the first house to DP. And now we're also going to initialize the second house to DP. And we're going to choose between the two. And here you can see where we have num2 and 7. And we know that 7 is greater than 2. So automatically DP has 2 and DP1, index 1, has 7. And this is the original array that we're providing. So again, here we're going to get into the for loop. And now we start step 1. It's going to go to the maximum of 5. Range works from 2 all the way up to 4. 2 since that's the step we chose here, since we already have 2 houses already. And now we go into initializing each part of the tabulation. And here again, now the first step will be at 7, which is here, or we can take step 2, which will be at 9. And we're going to add 9 plus 2 because we are starting here, so that means we're going to skip. So 9 plus 2 is going to give us 11, which is here. And that's what we initialized the array to. And then again here we are doing the same thing, which should be either one step, which is 11, which is what we have here, and it's what we already started with, or we go from 11, which is here, or 9, and we do another step, which will give us 12. But in this case, we're gonna, actually, it's either 7 or 10, 7 or 3, which will give us 10. So we know that 11 is greater. So that's the reason we end up putting 11 here. So we went from 2, and then we went to 9, and then we will go to 1, which will give us 12. And so far, we did 2 and 9, which gives us 11. And that's what we got here. So now again, we got, since the highest number has been 11, that's what we're using here for DP if we had taken the previous step, which is 1. And again, 2, 9 gives us 11, which is what we calculated so far. And now we decided that we're going to skip, since that's the maximum number, and that's what we got here, which is 12. And that's the calculation. So either take one step or skip, and so far we have been skipping for this. And now the output is going to be 12 based on, as you saw, the calculation. And that's what this does. So now instead of using extra space to store results for all houses, we are going to optimize our solution by keeping track of only the last 2 computed value. One variable stores the maximum money robbed up to the previous house. Another variable stores the maximum money robbed up to 2 houses before. At each step, we decide whether to rob the current house, adding its value to 2 houses ago total, or skip it and keep the previous maximum. This reduces memory usage while maintaining optimal efficiency. All right, now that we understand the concept, let's implement the optimized DP solution. This is optimization space-wise. not runtime wise. So this will remain the same because we want to make sure that it's not empty. And this will remain the same. And here will remain the same as well because if it has one house, we're going to return 0, the index 1. We're going to rob that house. And here's where we're going to make the change. Now, instead of creating an array, we're just going to create variables. And here what we're doing is the same as we did before. So here it says that index 0, we're going to initialize it to previous second step. And for the previous first step, we're going to initialize it with the maximum. So maximum in this case will be the same as we'll show because we're going to go through the same problem. And then here it says now it's going to be the same range starting at 2 and the same number since we already did here. So again, all we're really doing is just conserving space in this time, in this situation. But we're still going to do the same comparison here where we're going to make a decision of to take one step or take 2 steps. So in order to do so, here we're going to say previous 1 as a way of saying we're taking 1 step, or we're going to do num_i here, and then we're going to see if we should have taken 2 steps. So we're going to look 2 steps back to get to the solution. And then here we're going to swap. So we got previous 1 and we're going to give, so previous 1 is going to be given to previous 2, and then previous 1 is going to get the current value. And the same way, we're going to return, instead of DP, we are going to return previous 1 because that's going to be the last value we calculate. Okay, so it looks like it passed our test cases, and let's see how it compares. So this one, the previous one, was very efficient runtime wise. This one likewise is also very efficient runtime wise. And it turns out that it's actually not as memory efficient as I expected. Okay, so now let's go through a quick example, or an example of the problem. So it's the same problem above, so we're not going to explain this since it's the same exact one. The only difference here is that we're going to initialize num0 to equal 2, which is here. And now we're comparing 2 to 7. We know 7 is greater. Working with the same exact array, but just a different way of working through it. Then we're going through the loop again. And here's where we're doing the same comparison between the previous number, meaning the first step, or taking 2 steps. And that will be 7 or 9 plus 2. So 9 plus 2. And that's why it says previous 2, because we're literally going and saying, okay, well, 2 plus 9, meaning 2 steps. And that gives us 11, and we know that 11 is greater than 7, so it makes more sense to take 1 step and then skip than it is to skip right off the bat. And we'll do the same step again. Now we're doing a swap. And then we're just going to go back. We're going to iterate through this until we end up getting our final output of 12. So the optimized DP is both time efficient and space efficient. Is what I was expecting. But turns out that the bottom-up approach of just using, at least here with Leetcode, the bottom-up approach was more runtime efficient. But in reality, because I did not use array, it should be more memory efficient. So the only reason it's not as memory efficient is probably because the problems that Leetcode is providing are small. But in the big picture, the optimized DP is going to be more memory efficient. And that's what you will see here, where the space complexity for the last one, the optimized DP, is going to be 0.1, whereas the space complexity for the bottom up using the tabulation is going to increase because the more houses you have to rob, the more you're going to have to store. Whereas here, you're only storing 2 values, so it's never going to change. You're always going to have a constant storage. Runtime, they should be exactly the same. I hope this walkthrough helped you understand how to efficiently maximize the amount of money you can rob using dynamic programming. If you found this useful, don't forget to like, subscribe, and hit the notification bell for more in-depth coding tutorial. See you next time.